All right, so if you recall, it's like we've been trying to establish the global convergence of an arbitrary one-step method. And where we left off was that we established an error recurrence of the following form, that the error at the n plus first stage is bounded by some multiple of the error at the n stage plus a local error term. Okay, so what you're going to do then is that we want to take this error recurrence and then establish some sort of inequality. It's like about the error at the end stage. Okay, and the way it's like one does this is through a lemma, which is called the Discrete Gronwall lemma. Okay, and so let me just state this. Let's say that you have a positive sequence of numbers satisfy the error recurrence, all right, which is that z at n plus 1 is bounded by some multiple of z at n plus an additional term b, okay? And you want this to be true for a greater than 0 and some b, which are constants. And if that's true, then you can establish the following estimates. Then the following holds that Zn is less than equal to b over a minus 1 multiplied into a to the n minus 1, okay, plus an z0. And it's easy to sort of see from this that this has an implicit assumption that a is not equal to 1 here, okay? So this is the case for a not equal to 1. And then it's also fairly easy to convince yourself that the a equals to 1 case isn't so difficult. And you satisfy an inequality which looks like the following, that Zn is less than or equal to n times b plus z0. And then this is the a equals to 1 case. Okay, so let's try to prove this, all right? Okay, so for the a equals to 1 case, this is relatively straightforward. So I'm going to skip that. So I'm going to skip that for now. All right, and so let's look at the a not equals to 1 case. As you might expect, what one very, very natural way it's like to prove it's like an inequality like this is to apply induction. So we're going to do this by induction. Okay, so of course it's like you have to establish it's like the base case, which would be n equals to 0. Okay, so let's say we consider the case where a is not 1. And n equals to 0. Okay, so the n equals to 0 case. And so if you check what that inequality is saying, is that z0 is less than or equal to b over a minus 1, a to the 0 minus 1, right, plus a to the 0 c0. Okay, so of course a to the 0 is 1, 1 minus 1 is 0, so this term vanishes. Okay, and then this a to the 0 z0 is nothing more than z0. Okay, so the inequality you have here reduces to z0 is less than or equal to z0, which of course is satisfied. So that's fine. Okay, so we're good here. So let's now start. It's like by assuming it's like that this inequality holds for the n equals to k case. So you assume that the inequality, let's call that star, holds for n equals to k. Okay, and then you want to establish that it holds for n equals to k plus 1. Okay, so let's just look at z k plus 1. Okay, so zk plus 1, of course, still satisfies it's like the single term recurrence, right? Zk plus 1 is less than equal to a times zk, right, plus b, right? And then, of course, what you want to do now is that you want to use the fact that zk satisfies this relationship star. Okay, so I'm going to substitute that. So this is going to be less than equal to, right, a times b over a minus 1, a to the k minus 1, plus a to the k z0 plus b. Okay, so going from here to here again, it's like you're applying, it's like this inductive hypothesis that the inequality holds in the n equals a k case. Okay, so you can expand everything. So this is, of course, equal to a times b over a minus 1, a to the k minus 1, plus a to the k plus 1, z0 plus b. And then you can collect terms, and you can show that this is equal to b over a minus 1, a to the k plus 1 minus 1, right, plus a to the k plus 1 z0. Okay, which is, of course, the case for n equals to k plus 1. So, so you proved the Gronwall, it's like lemma, it's like using induction. Okay.